Hi, everyone. Welcome to today's Tech Roundtable on the Yuga of cloud-native databases. This is going to be a wide-ranging conversation about how the world of databases has evolved or co-evolved with the world of applications and infrastructure, all in response to changes in the world, right? Changing customer expectations. And along the way, we're going to talk about whether we're going to answer the question that we started out with, right? Why does the world need a new database in this world of cloud native applications? Okay, that is the topic for today. Do you need a new database in this world of cloud native applications? If so, what should it look like and what are the needs of this database? So our guests on today's panel have decades of collective experience building and sometimes even operating iconic databases. So let's kick this off with a quick round of introductions. And I wanted to go in alphabetical order, but I realized that I had to go all the way to the third letter of the first names in order to get the alphabetical order right. So let's start with Kannan. Kannan, can you tell us a bit about yourself? And in your introduction, also tell us which databases you have personally worked on, like built or operated, and what you're currently doing.
Thanks, Suda. Hi, everybody. I'm Kannan. A very good morning to all of you joining us from India and other parts of the world. So good evening, good afternoon. Yeah, Suda, so I started working at Oracle back in '94. But if you were to really ask me which was the first database that I worked on, it was actually Postgres around '93, '94 in grad school. I took my database course from Michael Stonebreaker, we all of us did a small project in our course to add a little extension to Postgres. But soon after, so in '94, after graduating, joined Oracle, worked there in the database team for about 13 years till the mid 2000s. You could say I worked mostly on the languages or the upper half of the database engine, the language and the query layer part of the Oracle database engine. And also after Oracle did stints at Facebook working on distributed databases like Cassandra and HBase, putting those systems in production for some very fast growing applications such as Facebook Messenger. Worked at Nutanix for a little bit, not exactly in the database space, but still distributed systems problems. And then about 6 years back, started Yugabyte with my two colleagues whom I met at Facebook. I think you also asked about sort of the Oracle journey. Was that right, Suda? You wanted one of the questions.
Yeah, what are you doing right now? We'll get to the journey, but what are you doing right now at Yugabyte?
I'm co-founder, president, and mostly focus on R&D product and working with customers on, finding best solutions for their data tier needs.
Great, thanks, Kannan. Kapil, over to you.
Thanks, Suda. Everyone, great to be here. My name is Kapil Gupta. In my career, I have had the great opportunity to work on SQL Server at Microsoft, which later on became Azure SQL, and then Google Spanner and Amazon Aurora. Since Kannan mentioned, I kind of got hooked onto databases similarly in a grad school course at Don Battery at UT Austin.
Awesome. And Karthik.
Hey, folks. Yeah, so I am one of the other co-founders. Just like Kannan mentioned, I'm one of those colleagues he met at Facebook. Anyways, like my background, grad school, I couldn't quite decide between databases and networking. And so initially I went off to work on networking, right? Like, and wireless and all sorts of networking stuff, distributed systems, but of a different kind. And then came to Facebook when the first database I worked on was this database called a peer storage system or something like that. And it wasn't a very good name. So, we had to come up with a better name. And so we named it Cassandra and open sourced it. And, that's where I ended up meeting Kannan and subsequently worked on HBase, et cetera, and Nutanix. So Kannan and I have worked together for 15 years. And what was the second part? Second part was what I do here. Sometimes I'm not sure, but it's mainly about the technical direction for the company. I'm one of the co-founders. I'm the CTO. So that means product direction, where we're headed, and customers, and how we can help them with their use cases, right? The next generation of data challenges and applications that are coming up.
Excellent. I think between the three of you, you've mentioned some of the most widely used, iconic, defining databases that we're going to be digging into. To round out the introduction, my name is Srinivasan. I've been in enterprise tech for close to 2 decades now. Makes me definitely feel old. Started my career at Microsoft as an engineer, and my first exposure to databases was when I was interning at IBM Almaden, and they had this talk where the DB2 had just beaten Oracle in some TPCC or TPCD benchmarks, and they were talking about all the fine-tuning that they had done to make that happen, right, the feat. So there was a whole tech talk just about the things that they had done, and that was my fascinating introduction to this world of race cars in tech, right, like databases as race cars. So this kind of takes us all way back. Kannan, let's start with you. You worked at Oracle for over 13 years, and you mentioned a number of different teams. So which you briefly talked about some of the products. Would love to dig into that some more. Which part of the Oracle product specifically, and what did applications look like at that time, right? What is the worldview that Oracle was built for?
Awesome. My role, I primarily, like I said, I worked on the languages layer or the upper half of the database engine. I did a lot of work with Oracle Stored Procedure Language, PL/SQL, which was a highly portable language that ran on all the platforms. And back in the day, Oracle ran on like 80 different, you could say, platforms, a combination of operating systems and processors. And this was before Java. Today, we take portable languages like Java and Go for granted. But it was one of those languages, fully procedural language with static and embedded support for SQL in it. So that was a lot of my work there. But in terms of like the broader context of the question and the core thesis of what Oracle's premise was, if you go back to when relational data models became popular, starting from E.F. Cord's paper around 1970, where fundamentally it put forth this radical idea at that time that relations and simple tabular ways of organizing data was very powerful. And on top of that, how to query data, this whole language around SQL, the structured query language, those things came from some of the early research work at IBM. But interestingly, Oracle was the very first one to really bring to commercial market a fully commercial ready solution on this whole relational data model concept, and with SQL as the way to query and operate on that data, like extreme query flexibility, take away the, rather than users saying the how-to of getting to their data and the access paths, really declaratively specifying what they want and letting the database engine do and figure out the access paths, the best access paths, being able to add indexes. I mean, that was so powerful, right? And to this day, that SQL and relational data model has a holding power. But if one thing I would say, what has changed, or maybe what the state of the world at that time was, largely the data sets and the applications weren't too large. I mean, like, a 1 gig data set was around, mid 90s was fairly uncommon. So a lot of the data sets fit in a single node. The throughput and the apps needed, whether it was a supply chain app or a payroll application, a banking application, the number of transactions per second you needed, and so on, you could largely handle in a single node. So a lot of the design points primarily revolved around building systems for a single node architecture. But that led to a certain kind of like application design, monolithic applications. The entire supply chain service would be like one large monolithic application, all in a highly web-like data format, like tables with a lot of interrelationships and so on. But that was sort of those days, and and it's kind of like you can see a lot of things changing, and we'll probably deeper dive into some of those aspects of what those trends were.
Yeah, definitely monolithic applications, and I think at that time the database landscape was also a lot simpler. Right? You just had a handful of real viable commercial databases that broadly fell into kind of OLTP and OLAP buckets. And today, fast forward to today, you have over 380 databases that are being tracked by DB engines. Right? This can be bewildering for anyone who's kind of trying to pick a database for their application. Right? If you're a startup, you want to get going and you want to pick a database, where do you even start? So maybe Karthik, you can tell us, for someone looking at databases today, what's a good way, what's a good framework for looking at all these databases and thinking about them?
No, that's a great question. Right? So this is one of the questions that, Kannan, myself, Mikhail, like a lot of us, we thought real deep and hard about while starting this, before even starting to build a new database, right? Like why build the 381st database and, add to pollution in the database space effectively, right? Like is really the most key question. But in order to understand this, it's important to look at a little bit of the journey, right? The history of databases and how they evolved, right? Initially, as Kannan said, right, it was the relational model that became dominant. It was simple, it was powerful, it was easy to understand. Well, 50 years later, it still happens to be simple, easy, and powerful, but never mind that part, right? So as you started evolving with databases, right, there were commercial databases and then there were open source databases. Those are just different flavors, right? I'm talking about databases like SQL Server, Oracle, etc. And then I'm talking about databases like MySQL and Postgres, right? They're not really different, right? The first real difference you start seeing is when special purpose databases started coming up, right? Like you saw that the reason for the open source databases to come up was really when the web took off, and the web applications back in the late 90s, early 2000s were really a second tier application. It wasn't super critical. It was something that was done for convenience, niceties. It wasn't something that was super core and critical, right? And nobody ran business critical systems on the web tier back then, right? And so, nobody wanted to pay for commercial databases, and it just made sense to start using some database that's new but free and, start developing with that. Over time, the web applications became super important, and they started getting standardized, but the databases they began with, they became a part of the fabric. But pretty soon, what people realized was a couple of things happened. Firstly, mobile development took off. And secondly, the scale of data started increasing, right? So there was this one database that could do a lot of stuff. And slowly, as the data volume started increasing, you see that even vendors like Oracle, they started introducing Oracle RAC and Exadata and all of these type of larger distributed databases in the Oracle's queue itself. And equally, at the same time, this was about the time when we met at Facebook, like Kannan and myself, Mikhail, we started working on distributing data and in a database tier by ourselves, right? Like this was the Cassandras and the HBases. The important thing about the hyperscaler companies like Google and Facebook is that the API to the database can be quite simple, right? It is completely feasible to build half of the database features in the application side because these applications are simply massive, right? Like the usage footprint is huge. You're talking billions of transactions and petabytes of data. So it totally makes sense to build a lot of that in the application tier. And you can even squeeze some level of efficiency and performance by doing that, right? But in a general purpose database, I think what we realized as we went down this thing is every developer would come back and say, hey, could I have that secondary index, or could I have that schema change that's online? And so pretty soon we realized, they just want SQL all over again, except in a distributed manner, right? So that's on one side. Now, on the other side of the fork, you start seeing these specialized databases that start dealing with specific problems, right? Like documents, time series, white column, like all sorts of stuff, right? And with the explosion of data, you also find that databases started specializing in giving great value for analytical workloads and OLTP workloads. So there's multiple dimensions here, which suddenly caused an explosion of databases. Specialization, general purpose distribution, specialized distribution for transactional OLTP, all of this stuff. So pretty soon there's a huge tier of databases or pockets of databases. And to add on top of that, the existing databases that are pretty popular, people started building solutions on top of them. These are sharding and distribution solutions on top of them. And combined with these sharding and distribution solutions, you get another class of databases, right? Like this would be like the Citus and the Clustrix and a whole bunch of those type of databases. So pretty soon you're seeing the sprawl. Now we're entering the age, or we have squarely in the middle of the early stages of the cloud native app development age, right? So it's time to take a step back. And if you really want to look at databases, it's time to look at, is specialization really going to help you a lot or not? That'd be the first question to ask. Specialized databases will save you some percentage in terms of cost and give you some performance boost. But is that worth it? Like a 10% saving on say $100,000 workload, right, is like $10,000. The same 10% on a 10 million workload is $1 million, right? Very different whether you should go for one or not, right? So, and this is some of the hyperscaler lessons also, right? It depends on the footprint, how much you optimize. The second thing to talk about is, how are your cloud native applications evolving? It's important to look at that in order to figure out your database. And it's pretty clear now that there's going to be 2 or 3 classes of databases. There's going to be OLTP databases, transactional databases that give you really good cloud native transactional properties, OLAP databases that give you great cloud native but analytical capabilities. And both sides are trying to add a little bit of real-time features in the middle. So real-time analytical or hybrid transactional processing. So there's that gray area where new databases are coming up and existing ones are improving. But I would use that lens as the best lens to think about databases, the 380 databases, and put them in the specialized bucket, in the OLTP bucket, in the OLAP bucket, all within the cloud native realm, and then the non-cloud native databases that were built before the cloud. Like, believe it or not, even databases like Mongo that are pretty popular, they were built before the cloud, right? So it's important to look at how they're evolving and if they're catching up and keeping up. So it's just important to think about that also.
Yeah, that's actually a great way to think about, because the cloud is such a disruptive event. It's almost like, as far as infrastructure and applications go, it is like there's a pre-cloud phase and then a post-cloud phase. And that is a big shift in terms of how you build things. We are going to go back to Kannan's journey to Facebook. But before that, I want to tell people, folks, if you have questions, you've got kind of people who are database veterans, technical leaders. If you have questions, just post them in the comments. I'll be looking at the comment section, and we're going to be doing it kind of a virtual AMA, right? So if you have questions, just post them there. We can dive into any specific topic that you might want. But Kannan, back to you now. So from Oracle, you then moved on to Facebook. What changed in the apps world between the Oracle world and what happened at Facebook? And how did Facebook react to that? For example, did Facebook use any monolithic databases at all? What are some of the challenges? Can you dive into that a bit?
Yeah, I think from day one, one of the issues that these hyperscale sort of like web or consumer-facing companies like Facebook, Google had is their applications. They were, their user base was growing, exploding, right? And their requirements, the requirements that they needed from the database tier were not something that single node databases could handle, right? Especially the site-facing use cases. So from very early on, these companies relied on more, pulling together single node databases like MySQL and manually sharding it at the application layer. So they introduced a lot of complexity that the app had to deal with the shard management, how to distribute the data across different MySQL or Postgres instances, how to rebalance it as growth happened. Like if I started with 100 MySQL instances and had to go to 120, how do I do all this rebalancing? What is the downtime involved? How do I minimize the downtime? So there was a lot of operational jugglery that needed to happen to keep up with the scale. These were not systems that could have worked with, say, Oracle. By the time Oracle already had clustering, right? But Oracle's clustering was not designed for a commodity infrastructure. It needed, special purpose interconnect like InfiniBand. So this were more, and Oracle's clustering, maybe goes up to 8 nodes, 16 nodes, but it has a breaking point. Beyond, it's not really designed for the shared nothing architecture, if you will. And people use the term shared nothing versus shared disk. Oracle is designed for shared disk architecture, right? So that has limits on scalability. So I think that was the one very stark difference that was visible. I think the second trend that we were seeing is that the fast growing applications were putting a lot of pressure on the database tier. So one way that we were solving the problem is by fronting the databases with a cache so that a lot of the load could be offloaded from the database, but that introduced complexity of its own kind. Like this was hard enough to deal with in a single data center. If you needed to serve data from multiple data centers and multiple caches, the app level complexity and the operational complexity to maintain the data and cache coherency across multiple geographies was just becoming too intense. And that's why we started investing in distributed databases that could keep up with the pace of the fast growing applications, right? And we worked a little bit on Cassandra for a couple of use cases. We did a lot of work on systems like HBase to power applications like Facebook Messenger. But the common theme was, hey, it'll be great if the database itself is designed to be cloud native, can run on commodity hardware, can be horizontally scalable, is resilient to failures like node failures, data center failures, and so on. But this first generation of solutions also took shortcuts, right? And the main shortcut that it took was it compromised on the API richness. Like these NoSQL databases exposed much less of a API to the app developer. because they were focusing on just distribution, load balancing, sharding, and doing all of those things automatically. Nevertheless, it was very successful. I mean, like we put many production applications on these systems, and greatly simplified the scaling and the operational band-aids that had to be done in powering applications like Facebook Messenger.
Awesome. That was completely different worlds in some ways, right? They built for. And there was a question that I think is very relevant that came up on LinkedIn. So how much is Oracle RAC designed for a real world requirement? It seems to be the main blocker for legacy customers looking to modernize their database estate and infrastructure. So I'm trying to understand the question. Is it how much is Oracle RAC a real world requirement? As in, maybe we could frame it as what was driving Oracle RAC specifically, right? Did Oracle RAC kind of come about in response to some kind of real world customer requirement? If so, what is it?
Absolutely. See, while Oracle started with the single node architecture, and that was say in the 80s, right? But over time, the customer expectation was like, hey, can Oracle support more scale requirements? What if a single node cannot match the throughput needs or the transactions per second requirement of the application? So Oracle was at a crossroads in deciding which way to go in terms of a distribution strategy. Should they go with a shared nothing architecture or stay with a shared disk architecture, but introduce clustering, right? So eventually Oracle picked at the course of staying with the shared disk architecture. And that's what Oracle RAC is. There are multiple nodes in an Oracle cluster. They still share a common storage substrate, and they are connected by InfiniBand. But ultimately, the real world requirement was the need for scale. It took an approach which has served it quite well. It can scale to a great extent, but not to the extent where the market needs. I think it did well for the 90s and the 2000s, but as we're entering the 2020s, the OLTP applications of not just web scale companies, but then the next startup that's building, say, a DoorDash or an Uber Eats like application is needing their OLTP database tier to be highly scalable, and the kind of requirements at this day and age are not going to be sufficiently addressed by a shared disk architecture.
Yeah, for sure. And there are a couple more questions we're going to get to, but Kapil, you've been very quiet on this call, so it's your turn now. Your career in some ways kind of spans this evolution that we just talked about, going from monolithic RDBMS to web scale, cloud native. So you went from working on SQL Server and then from there to Spanner, and from Spanner to Aurora. So can you tell us the design considerations for each of those databases, right? SQL Server, Spanner, and Aurora, and how they are different, right? What's the difference between them in terms of how they were designed and what they were designed for?
Yeah, absolutely. So that was a great question. I mean, I certainly consider myself very lucky to have worked in these amazing products. I spent 10 plus years in SQL Server, which was a great learning experience, a great foundation on how to build single node databases. And then I remember kind of reading the Spanner paper and being just blown away by it, right? And I'm sure everyone on the call knows, but just in case, Google Spanner is Google's distributed database service. It was the world's first horizontally scalable SQL system, but built for Google's internal use. And I remember when I joined Google Spanner, it was more like a storage subsystem. The code had just been forked off of Google Bigtable. But over time, more and more of Google groups, like Google Ads, and of course Ads is really big in Google, but not just Ads, YouTube, Google Play, which is the Android payment system, all of it started getting built on Spanner. The majority of the metadata of Google Cloud started getting stored in Google Spanner. And I would say the design points of Google Spanner reflected this journey. Right? In my opinion, the design points were scale, it was massive scale, Google scale, was one design point. And in order to meet that scale, not only the storage, but the query system, the query optimizer, everything had to scale, right? The schema management system was very innovative, right? So scale was one design point. Another design point was resilience. The joke was a data center would go down and the spanner engineers wouldn't even get paid because, so what, the software is supposed to handle it, right? And then consistency, right? And here's the example I would give is Google Spanner offered serializable isolation level, but nothing else. Like, why bother? Kind of was the mindset. Right? And later on in my career, I switched to Amazon Aurora. And the reason I switched is because while Google Spanner was very successful within Google, it felt like Aurora was very successful externally. And Amazon Aurora was Amazon's fully managed distributed data as a service, and its origins were very different. It kind of grew out of Amazon IDS, and it offered MySQL and Postgres as a service. And I would say I learned quite powerful lessons when I went to Aurora. One lesson was the power of open source. Up until then, I had been working in proprietary systems, so this was very eye-opening for me. The second lesson was that, in my opinion, Amazon Aurora very consciously thought about not only where it should innovate, but also where it should not innovate. For instance, it didn't do much innovation in the query layer, in the API layer. It left it alone, which gave a very comfortable, familiar experience to the developers. Right? And I think the third lesson for me was that everywhere I looked in Amazon Aurora, this famous Amazon customer obsession principle was there to see. Right? Everything was very, very customer driven. And all those lessons have stayed with me.
Awesome, Kapil. Thank you. And you touched on resilience, you talked about scale, you talked about Postgres and reusing API layers, and all of these are going to be relevant for our conversation as we go forward. Right? These are the things that drive people to go and build a new database. Right? It is resilience, scale, geo-distribution is another one that comes up often, right? But these are the things that the old world just could not deliver on. So Karthik, when you built, and you, Kannan, and the team built Cassandra and HBase, what were the design considerations that went into that, right? What are the requirements you designed HBase and Cassandra for?
Yeah, I think, it was simple, right? Like when we started, building Cassandra, or what eventually became Cassandra, we were doing this for just one application, right? The application was inbox search. So Facebook back then had a way for people to send each other messages. You can think of it as a lightweight, Gmail kind of thing, like lightweight inside the Facebook app. And then there was chat, and there was many other ways to communicate with people, but sending messages was one of them. And there were about, I'd say, 100 to 200 million messages a day being exchanged between people. And there was a big complaint, though. No one could search through their messages, right? We didn't have a search index. Now, this was a conscious thing because the Facebook's sharded, the MySQL tier that Kannan was referring to, it had really high grade hardware, right? So it wasn't like the InfiniBand of Oracle. It wasn't that great, but it was still like a SAS drive, and it's still expensive stuff, right? Like you don't want to take that lightly. And it had a lot of operational people watching over it, right? The problem with search as an application is that it's extremely write heavy. The data sets are pretty big, and it doesn't get read very often. So kind of puts this weird challenge where your operational burden and footprint and your hardware footprint increases a lot, but your usage decreases a lot. And it's still useful though, right? So if you can find those two messages when you want to, they're really a useful feature to have, right? So this problem nobody wanted to solve because nobody wanted to put this in the MySQL tier. And some of us, we realize it requires a fundamentally different thought process. Can we support this on commodity hardware, right? And no database back then could inherently distribute data and computation, transaction processing. So everything was a single node, and you had to figure out how to shard in the app layer, and that was just too expensive. So we ended up building a database, and again, we also explicitly thought about how are we going to survive data center failures. There was a big drive to do that back then, and how are we going to keep it operationally simple and just no touch, right? So the famous CAP theorem hit us, and you can only do so much. And we said, search index doesn't have to be consistent. If somebody complains that they can't find a message, you can go get their messages and reindex them, and voila, you're back in business, right? So why overthink a problem? Let's go solve it with a highly available database, which makes operations simpler. And you can give up consistency, that's fine. But partition tolerance is important because you're now going to have to operate across data centers. And secondly, we were just building it for search, right? So we could do whatever we wanted with the database API as long as it worked for search. That was the application that would be success for us. So we went ahead and built this database, Cassandra, what we eventually became Cassandra, open sourced it, and so on, right? Now, the next thing that Facebook did was it unified all messaging. It said like chat and messages and email and everything, just put it into a single system. Now, suddenly that became the system of record. It's no longer like, okay, if some message is missing, you can go pull it from some other tier. This is the tier that would store everything, right? And because we were putting in chat already had a much larger volume. It was an in-memory system that was maintaining 30 days of history. That was a much larger in volume system. So, and it had to be more real time. So we had to rethink our database choices. And then we said, we searched far and wide, and then we picked HBase for a number of reasons, primarily because we wanted consistency. We were okay with trading off availability a little bit. And we said we'd put a caching tier on top to simplify the availability problem. And we gave up on the multi-data center, completely seamless stuff because consistency was important. Okay. So, but even here, the API was its own custom thing. It didn't matter because, we were working hand in glove with the team that would use us on top. And, just some simple API that people could use and very custom would suffice, right? The drivers here. So when we opened out, or when we were building HBase, we had no idea what the final product would look like in terms of usage. Well, it turned out that when we opened the curtain finally, it was about 20 billion messages being exchanged, right? So we'd gone from 100 to 200 million to about 20 billion, right? Like, so it's a huge number. And we said, like, you know what, if we can scale for this much, we should be able to do the search index too. So we moved the whole thing in here. So it's like, why deal with two systems and more complication, right? So we moved the whole thing here. And, that journey taught us about, how to really operate these databases, how to chase the mythical 5 nines, why 5 nines is not a good metric, and what else do we do, all of that stuff, right? But then then the data centers inside Facebook started evolving, right? We had the equivalent of zones and regions and people being data being distributed all over the place and decommissioning. And so the cloud nativeness started hitting us more and more. SSDs had come out. So when you put all of that together and you looked at the HBase design, well, it was still retro, right? It's not really the design built for multi-region, multi-zone, and SSD type deployment. So we said we had to go back to the drawing board and do it. And that time, Kannan and I left. We were working on the next generation, but eventually a system called ZippyDB got put into in production in Facebook with that type of a design principle, right? Well, some of the leads from one of the lead engineers from ZippyDB is with us here at Yugabyte because the architecture is quite similar. But to extend this journey a little more, public cloud economics also work differently, right? Like from your regular. So there's a lot of these type of changes that you have to accommodate in building a database for the cloud.
Yeah, no, this is, and you talked about this notion of building a database for a specific application, which I think a lot of first-gen web scale systems did, right? They basically built the database because they were trying to solve a specific problem that an application had. I think the question then was, how do you take that and build something which is more of a general purpose system from that? We've had a number of really good questions come in while we were talking, so I'm going to read out a few of them. I'll just throw it out to the group and any of you can jump in. So the first one is, the first one is Aurora, Azure Cosmos DB versus Amazon Aurora. Can we comment on architecturally what are the differences and just more broadly, what are the differences between the databases? And keep it at a high level, right? We don't have to get into the details there, but what are the differences there?
It's got your name on it, Kapil.
Yeah, I can take that. So and Karthik talked about DB specialization, right? So this is kind of in that arc. So in terms of Cosmos DB is more like a NoSQL database. And I think the closest competitor in the AWS landscape would be DynamoDB. Whereas Amazon Aurora is a SQL relational database. So the space where Cosmos DB innovated, a couple of things I would mention. One is that on a single storage layer, it built multiple API, right? Like MongoDB, various kinds of API, which became really popular. And the other thing is it also provided a dialable consistency model, like all the way from eventual consistency to kind of higher level of consistency. So both of those were pretty key innovations that Cosmos DB did.
That's a great point. Yeah. So the next question is, do we still maintain cache on top of each single instance of database? If yes, then cache coherency will still be the problem here. How do we address that?
Yeah, happy to take that.
Is that related to sharding? Is that the sharding related question?
But I think you should answer it at two levels, Kannan. I think
Yeah.
we should answer it at the application level. Do we maintain a caching tier on top of the database? That's one way. And the other way is, do you have a caching tier in the database nodes itself, right? So there's two ways to look at it.
Yeah. So, what we find is most of our customers find the direct performance of Yugabyte good enough that they're not fronting Yugabyte with the cache. That was actually a design philosophy, that we wanted to build a high performance database which will give you basically single digit millisecond latency right out of the box, right? But to get there, yes, there is a lot of caching that happens behind the scenes in the database layer itself, right? And we find that people rarely are fronting Yugabyte with like a Redis cache or an Elastic cache. Now, in terms of the database itself, if your question is, okay, if you're running a 10 node database, are all the nodes caching the same blocks, and is there a cache consistency problem? The answer is by default, no. Each node is responsible for some portion of the data, and you have caches that are specific to the portions of data that node is serving. But there is replication going on underneath the system. So you may ask, like, what if I try to read from a local data center, from a local replica? Are we doing duplicate caching? Yes, there can be duplicate caches, but the whole model is kind of a log structured data model. We never overwrite the same blocks. Blocks are immutable. Their version, there's multi-version concurrency control. So that makes it easy to cache it at multiple nodes. But it is not the case that a block is cached on all 100 nodes. Typically, it's just on the node that is the leader for that particular shard, or if you're doing replication, maybe like, it's cached on 3 different nodes, but not on all the nodes.
Awesome. Anything to add, Kapil or Karthik?
I think that was a
fun problem to get to
So I'm going to, there's one other question that comes up very often, right? Because almost every week we speak to a customer who's trying to manually shard their database right now. And this is still the prevalent practice among startups, right? They start with MySQL, start with Postgres, things start scaling, and then they start sharding it. And before you know it, they have a team of people who are standing up the sharded database. Gives you awesome performance, but what are the problems with sharding? If you are a startup and you're thinking about sharding a Postgres or MySQL, what are the problems and where should you draw the line?
Yeah, I can take this one. I guess it's just a round robin. So, okay. So I'll go through the Facebook journey, right? Like Facebook did end up manually sharding their databases, but that was because there wasn't a choice back then, right? Like Facebook's manual sharded database tier came into existence even before the first NoSQL database was built, right? Like, so there was really no choice, right? But if you think about the first problem that hits you when you try to manually shard, it is about how do you shard your data, your sharding strategy, right? There are 3 or 4 legitimate strategies to shard data, and each with a different set of trade-offs, right? So the first thing you can do is you can take each of the, let's say you have a bunch of users, you can take each of your users and put them on a specific node, right? You can kind of say, I have 10 nodes. I'm going to take the user, I'm going to modulo the user's ID or the hash of the ID by 10 and put it on some node, and then I'm going to keep going on, right? The problem with this kind of a strategy is when you add a new node, you have to shuffle data all over the cluster, right? So it's going to be really poor to rebalance data. So that's going to be the first thing you hit. Now, what you'll realize after that is, okay, you can't just shard it and assign it to a node. You have to shard it and have a logical shard ID, assign it to that shard ID, and assign the shard ID to a node. Now, this type of an approach brings up the next logical problem, which is like you have to keep track of these logical shards, right? You have to keep yet another central database of metadata of how users are mapped to shards and shards are mapped to nodes and at what point which shard lives on which nodes and so on. This problem is further complicated by the fact that you probably want availability and on failures, right? So it's not just a shard belonging to a node, it's multiple replicas and which shards and how do they live and so on. And the minute you have introduced multiple replicas, you also need to load balance, right? You don't want all of the slaves sitting on a node like the secondaries and all of the primaries sitting on a different set of nodes, and the primary nodes are hot and the secondary nodes are just running light. You need to balance them across, right? So that brings up the next level of complication. Now, let's say you keep going further. Now, there is a particular evolution of your application that comes up that needs to do indexing across these shards, right? How do you deal with that problem? Well, you now have to like completely rebuild a routing layer. You have to build a layer that will understand how this index has to get built on top of all the shards in a completely independent system, right? So that's going to be another problem. Now, let's say there's a query that comes up that has to lexicographically query data between shards. Like, in some examples, you may want to say, give me all cities that exist between A and E, right? Except you've sharded your data away, so you don't know which shard lives where. You just know that given the name of a city, you know which node to find it in, but you don't know how to find all the cities between A and E. So you now have to fan out and incur terrible performance, especially at scale, right? Like so there's a number of these type of problems you start running into, and I am talking so far about architectural problems, right? Then you get into the next set of problems, which are about operational problems, right? Think about in the 5-6 years that Yugabyte has existed, relatively short time, Amazon has come out with 4 different SKUs of machines, and so have the other cloud providers. You have all the C3, C4, C5, C5D, NVMe, and like locally attached as EBS. So your application keeps morphing, right? So what is important to remember here is, in order to keep the ROI good, you have to keep moving the data to newer and newer type of machines. And that means every shard, every replica, every assignment, you'll have to keep moving it while your application is running, right? So, and then there's AMI refresh, software upgrades. There's a whole bunch of stuff that you'll have to deal with operationally in order to roll through your shards and so on and so forth. So this problem really starts getting amplified every step of the way, right? And you will lose relational features while doing it in terms of manual sharding. And so these are the precise reasons actually why we came up with a database like Yugabyte DB, because sharding is the path to, you want to start small. And if you start small, you have to be able to scale. And if you want to do bursty workloads, like seasonal workloads, like retail has like a peak season at the end of the year, you have to be able to scale out and scale in, and replace the machine types and go through AMI refresh and all of that stuff, right? And then, not to mention, now you want geographic replication of data, which is very complicated in a sharding system. So hopefully that gives you a flavor for some of the complexities of manual sharding.
That gives me more of a full taste. I mean, flavor is like a deep dive taste. So I want to keep the conversation moving, because there's another piece to this, which I promised in the beginning around how applications have evolved and such. But there are a lot of questions. Folks, if we don't get to all your questions, definitely join our community Slack. Kannan had posted a link up there. We can post it again. Join the community Slack and we can continue the conversation there, right? Because we want to make sure that all these questions are answered. So Karthik and Kapil will be available. I'll also be hanging around on the community Slack. So Karthik, and now from there, you went on to start Yugabyte with your colleague Mikhail. Why? What did you see in the market that was interesting and attractive? This was 6 years ago, so it's been a good journey so far. So.
Yeah, I mean, maybe I'll start. I think Kannan, you should also add. Right? So, yeah, so I think market is so the funny thing about starting anything, whether it's an open source project or a company, is yes, you have to have this crystal ball to peer into the future, and which you don't. So it's effectively really taking a bet, right, on a direction. But I guess the question really is, what was our rationale that made us think like, man, this is actually a very sensible bet. Let's risk it all and go do this, right? I think that's really the question. What is that set of bets, right? So what we saw like in Facebook was, you can kind of simplify it saying there was a fork in the road, and each fork was developing in its own direction, right? One fork was the MySQL tier and manual sharding and how that went forward, right? So the journey there was, the app was rewritten a couple of times in order to go like I just described sharding, right? The physical attachment to node, and then the logical shard, and then you find that the logical shards are not distributed properly, and so you have to operationalize that. So we went through that entire pain, right? So you could think of Facebook's sharded MySQL tier as a very large distributed SQL system that they built in an operational manner with code, with applications, with operational people, and so on. And then went through different types of hardware, right? Like went through SAS drives and SSDs and NVMe, and just went through the whole thing, and then a disaggregated rack architecture. So they went through that whole journey. And they found that the database itself, like MySQL, was a B-tree-based system, and that didn't work really well. So, we were in HBase, we were able to do like almost a 1:1,000 memory to disk ratio, the amount of data stored to amount of data you could serve. Whereas the SSD tiers and B-tree-based systems could only do 1:4 or 1:10 if you were lucky, right? It was around that ratio. So we wanted the same algorithms on the other side, but found that with SSDs, Java wasn't a good a good language, right? GC would really hit you. So, and all of the systems we had worked on, Java, like HBase and Cassandra, were in Java. So we ended up building MyRocks, right, as a plugin to convert the MySQL storage tier to LSM that Kannan was just mentioning, right? It's a log structured merge tree system, so that you could serve more efficiently on an SSD tier with better automation, better replication, and so on, right? And then there were a whole bunch of advanced systems, like, for example, Wormhole, this, that, which would do distributed caching validation so that you would have it as a serving tier in a geo-distributed fashion. That was one path, right? The second path is the path that we described, that, Kannan and I have actually been on this journey where, we built the first set of federated databases, like, Cassandra, and then HBase, and how we did it for scale, and then ZippyDB, which is transactional. But the API tier was like, it's just a set of APIs, right? It's like RocksDB, right? Just a get and put and key value and whatever the API we could come up with, and whatever suited our fancy that day. It didn't matter. It's like, we just work with the application development. That sounds great. Let's put a column family. Sure. Like, it doesn't matter if nobody understands it. We can keep talking to them, and everyone's technical. Everyone likes to read the stuff. But the problem is, in order for the database to become general purpose, these two paths would have to merge, right? So these two paths, on one side, it's LSM, sharded SQL with global transactions, and all of this invalidation and serving tier and geo distribution. And on the other side, it's built-in sharding, built-in scalability, availability, and horizontal, like on demand, all of that stuff, but without the language capabilities, right? We had to marry those. So and when we looked at the market, right, and everybody will tell you 380 databases, great. If you're building a transactional app, what would you pick? Well, it turns out the 380 becomes two. It's MySQL or Postgres. And if your application is cloud native, what would you pick? Well, it turns out neither are, right? So it's just a very simple question, right? If you want to build a transactional app and you're picking Postgres, right, which is really clearly the winner right now, well, you pick Postgres, but how are you going to ensure that it can scale when the time comes and be available and resilient and all of that? So that was the singular question, which is effectively these two forks that we were talking about also, that led us to starting this database project. And the company is formed around the project. So.
And maybe
and it is open source.
Maybe I'll add
go ahead.
some color tying into a question that came in also. The question was again like between shared nothing and shared disk architecture. So maybe just to recap, let's call shared disk architecture an architecture where all nodes in your cluster have to have direct access to that storage substrate without like forwarding and so on. And usually to do this, you're building on proprietary infrastructure, like I gave InfiniBand as an example. But modern cloud, whether it is private cloud or public cloud, is a shared nothing architecture. Why do we call it a shared nothing architecture? Because each resource or node, if you call it, or server, has its own compute, own RAM, and own storage. So it shares nothing with each other than connected on commodity, TCP/IP network, right? So that's what modern cloud is. And whether people are going to private cloud or modernizing their public cloud, the underlying infrastructure is this commodity building blocks. And to connect the dots with the Yugabyte journey, firstly, recognizing that OLTP workloads are getting big. They're no longer, they need clustering, they need distribution. That is number one. But then this choice that people have to make, either go with NoSQL solutions like DynamoDB or Cassandra, which are eventually consistent. They are not transactional. That means you give up a lot on app productivity and rapid application development, or you go with something like MySQL or Postgres, but then you give up on scale and elasticity. So our mission was, can we build something that can address and solve these two needs, right? And that was really the thrust behind starting Yugabyte.
Awesome. Thank you, Kannan. And Kapil, to round out your story, you then moved from Aurora to Yugabyte. You joined the Yugabyte team. Why, and what is the motivator there? What did you see in Yugabyte and Yugabyte DB?
Yeah, absolutely. Basically, a mutual friend kind of introduced me to Karthik, and then I, read his blogs. And I mean, I'll be honest, the more I read the blogs, the more I felt that the co-founders had gotten some key decisions right. And, given sort of my background, it felt like the best of Spanner coupled with the best of Aurora. Like the storage was literally seemed to be inspired by Spanner. And some of the principles there, like, scalability, no single point of failure, resilience, all of that, right? And the no proprietary API kind of mindset from Aurora, right? So all this really resonated with me. Another thing that resonated with me is the fact that Yugabyte is completely open source. Before joining, I actually read the code from outside and the storage code at least, and to my great surprise, it made up, like, because the storage code is never simple in databases, so the layering and all that made sense. But by far the biggest reason was the co-founders themselves. Like, I've been super impressed by their technical, both the technical but also the product leadership at Yugabyte, and that's the biggest reason.
Thanks, Kapil. Yeah, that's a good point. I mean, we talk about Spanner below and Postgres and Aurora on top, right? It's kind of a database that takes the best of Aurora at the upper half and Spanner in the lower half. So that's a great point. I know we have eight minutes left, and there were two big areas that I definitely wanted to touch on. The first one is, how have all these changes in customer expectations and user and even databases, how has that changed how applications are being built, right? If you're a developer and you're building your application for your next $1 billion startup, what has changed in the application world? Karthik, do you want to start?
Sure, yeah. So, okay, so firstly, if you think about what was the bottleneck before, the bottleneck was racking and stacking hardware, right? Like I remember at Facebook when we were building Cassandra, right? We just ordered a whole bunch of machines, and they said, how many machines do you want? And we said, we don't care, just like maybe 50, don't care. If it's more, somebody will take it. If it's less, well, we're screwed anyway, it doesn't matter, right? So, because it would take 9 months to a year to get those machines, because that was the backlog. And I mean, we knew we could build the database by that time, but we didn't know what we were looking at. So it's just like very tough, right? That used to be the problem, right? And in 9 months to a year, you can do a lot, right? Today, the cloud has really democratized that. It's like, it's minutes, right? You can get all of these machines ready in whatever configuration you want. And so that immediately shifts the bottleneck in a big way to app development, right? So you can't do anything practical in 9 minutes with respect to app development, not 9 minutes, in a couple of minutes with respect to app development, right? So now it's come down to people thinking really about, how do you deploy quickly? How do you build quickly, like build the app itself quickly? How do you address scale needs without taking, you don't have the 9 months to go and figure out how to scale. You have to do it immediately, right? Like, so your application comes out and you have to be very worried about a phenomenon called accidental success. It happened all the time at Facebook. You build like 50 apps, and 5 of them will become incredible successes, right? And so as database engineers, we would get asked, okay, this app really succeeded. Can you roll out to everybody in the next week or two? Well, everybody is 2 billion users, right? Like, guys, like 2 billion users is a lot of users, right? So, but the point is, that's really what you're looking at. If it's not 2 billion, it's still a lot, right? Like, so you have to be able to scale up very quickly. And if the application doesn't perform well after a while, we have to scale it back down and say, you know what, don't let too many resources, let me go on to the next thing, right? So that's the nature of app building, which means your application API should be simple and powerful from the database side. At least I'm stick to the database perspective here. So you should be able, it should be a standard API. You shouldn't have to learn too much. You should be able to quickly use the database's power, like, leverage that in the way you want, do a CI/CD, get it into production, and handle a variety of scenarios, including downtime scenarios, upgrades, scale scenarios, replication. So the database has to now do more, right, in terms of giving you SLAs, giving you features, giving you a simpler way to use, and so on, right? So that, I would say, is really the biggest shift that has happened, right? So, but yeah, I don't know, I'm sure
Awesome.
other folks have.
Kapil and Kannan, where do you think the biggest changes have been if you're a developer?
I mean, I would say, in some sense, the expectations around ease of use is through the roof. Like, and I would say ease of use and simplicity, both in the operational dimension, but also the developer friendliness dimension. Right.
Awesome.
Like everything, those I feel have been a sea change. The bar is just so much higher now, and like a big reason why Snowflake succeeded, in my opinion, is that they're just so much easier to use.
Yeah.
And the other thing is, I mean, this is a much talked about point in the industry, that apps are no longer, they might, like, if you think of even Facebook as an app or any company, there are so many micro apps within, and each one have their own delivery and rapid delivery timelines, right? So yes, maybe the databases themselves, like when we were working on HBase, we were only pushing new versions of the database to production once in 3 months, but even that was quite uncommon. But the app tier, there were daily pushes, right? And each, like whether you think of the news feed as a microservice or a photo storage as a microservice, they were just like constant incremental changes happening. So this whole CI/CD mechanism, the real-time delivery, that has needed these large applications to be really broken up into subparts that can be independently released and delivered, right? And all of this has sort of needed a fundamental shift in designing the entire stack end to end, and that includes how you test the database tier also along with it for compatibility, schema evolution. So it keeps pushing the envelope on what is expected from each of the tiers.
Yeah. One of the things we have seen is this democratization of development, right? You have all these new frameworks, all these new, things like Next.js that are every week I hear about a new JavaScript framework, which means there are a lot of developers coming on board. And the biggest ask there is just give me a database that works, right? So there's a reason why we are seeing cloud databases really take off, because they allow developers to just get going in seconds or minutes without having to think about how they're going to deploy, manage, and all of that stuff, right? Now, I know we just have a couple of minutes, and I want to touch on, as teaser topics for future sessions, folks, we're going to talk about serverless. Karthik, what even is a serverless database? We've been hearing about serverless so much. What is it?
Yeah, it's a overused term right now, but yeah, I think okay. So there's a couple of ways to look at serverless. So serverless can be a billing payment model, or it can be a consumption model, or it can talk about the underlying infrastructure. So that's three different meanings of the word serverless, right? So broadly, what it means is if I'm using a certain resource, like it's in the case of a database, if I'm using the database, I'm going to pay for it. If I'm not using the database, I'm not going to pay for it, which means the usage, as soon as I stop making requests from the database, my cost goes to zero. If I start using the database, I start paying for it, right? That's the highest level definition. But like I said, this means three different things, right? The first thing it means is I have an application that will start and stop, right, in the simplest ways. Or in another way, I have an application whose usage will go up and down, right? It need not stop. It can go up and down. It'll vary, right? So just charge me for what I consume, right? Like don't charge me for my peak, which is how you do things. So you go in provision saying, I think in the worst case, I'd need 100 cores. So let me go and make a 100 core database. And yeah, I get charged at 100 cores, but most of the time I'm just using, on average, I'm just using 50 cores because, most of the time I'm at 25 and sometimes I'm at 100 and the average comes out to 50. Well, guess what? In the cloud, if the database is really scalable, you can actually charge people for just 50 cores, whatever they use, and you can scale with the workload. So that is the consumption model, right? If you talk about the pricing model, that is like how you charge. That also often falls under the serverless umbrella. Is it by the number of requests I make, the number of rows you return, the CPU you use, the network you transfer? There's a whole bunch of stuff underneath, but it is how you do the billing, right? Like the exact mechanics of that is also called serverless sometimes. And a third definition, and this is my personal favorite because it makes it a little easier, at least from the world of databases, is that the infrastructure underlying the application, right? Like in this case, the database infrastructure is constantly mutating, right? Like, so there is no notion of coming and saying, I am setting up a 3-node cluster of 16 cores. It doesn't mean anything because 2 minutes later is something else, and another 2 minutes later is something else. So it is serverless in the sense you're not thinking in terms of servers. You're not thinking in terms of there's 3 servers and 16 cores and that's my cluster, because that's how you used to do it before. But with the cloud, you think serverless. Your application gets whatever your application demands are gets satisfied, but you don't think about how many servers across, how many nodes, how many cores. You don't care, right? So I'd say it is a very valuable way to think in the cloud, except the term is getting applied for everything, right? So
architectural versus consumption model. That's awesome.
Yeah.
I know we are at time now. It's 9:30. So Karthik, Kannan, Kapil, thank you so much for this awesome conversation. We are going to be doing more of these roundtables because it sounds like there's a lot of interest in diving into these topics like edge and IoT, talking about serverless some more, talking about auto scaling and auto tuning databases, cloud databases. So there are a lot of topics that we can dive into. Folks, a couple of reminders. I've seen quite a few questions come in. We tried to get to as many of them as we could. If you have additional questions, join our community Slack. That's where we continue these conversations, typically from these tech roundtables. And the second is, we have a cloud DBaaS offering. So just go to cloud.yugabyte.com, sign up and give it a try. It's available, it's free. You can just get started and give it a go. Let us know what you think. A lot of what we discussed here will be relevant when you try out the product. With that, let's close. Thanks, everyone. Thanks for joining us.
Thanks, everybody, for joining. Thank you.
Thank you, folks. It was fun. Yeah.